In this video, we will look at an ad hoc problem that involves operations on a subarrays. These kind of problems are becoming increasingly famous on codeforces, and these are the kind of problems that requires no data structures, no algorithms, no fancy tricks, just pure thinking and reasoning skills. So if you want to improve on these kind of problems, make sure to watch the video till the end. Let's start with the simplest version of this problem, which does not involve a subarray. You are given an array, and in one operation you are allowed to select any index I. Suppose you selected this index, then you can either convert this element by applying the modulo P or applying the modulo Q. So P and Q are given to you at the start and they are fixed. Not only that, you can do as many operations as you want. You can do infinite number of operations if you wanted. And you are also allowed to select one index multiple times. So for each index, you are allowed to do infinite number of operations. And in each round, you have independent choices. So it doesn't matter that in the previous round you did a modulo with P and now you want to do a modulo with Q. You are allowed to do that. So you are free to do anything that you want as long as it's just a modulo with Q or a modulo with P. Now your goal is to minimize the total sum that you get after doing all the operations and you are satisfied with all the operations that you have done. So how do you solve this problem? So to solve this, of course, you have to notice that each index is now independent. Why? Because each index can independently minimize itself. So let me write that down. This is the first observation that you can make. Each index is independent. This means that you can have a local maximum at local minimum at each index. So we can have a local minimum. So this means that if you want to overall minimize the global sum, you should minimize each entry. So let's see how to minimize each entry. So you can already see that we were dealing with an array, but given the constraints of the problem that you are allowed to select one index multiple times and you are also allowed to do this operation as many times as you want, you can now focus your attention on just one single element AI. So what will the answer be for a single AI when there are no constraints that exist? So let us explore that. So you have AI, and in the first operation that you do, you can either go to AI modulo P or AI modulo Q. Right? These are the possible choices. So you have to consider both the choices and pick whatever is the best. But whatever is the best might not necessarily be the one that you retain because you plan to do this operation many times on this element. So this is also one of the learnings, that just because this gives you the smaller value doesn't mean that you have to stick with it. It is possible that this gives you a larger value, and then repeating this operation again might give you something much smaller than this could have provided. So now let's wonder what happens when you apply the operation second time. So this is the round one. Round one, you must have applied this operation and you will have reached either this state or this state. So from this, again, you are allowed to do two independent choices. You can either go to AI modulo P and then the entire modulo P, or you can do AI modulo Q. Sorry, you have to start with the element that you are given. So that would be AI modulo P, and then at the end you apply a modulo Q. And where can you go from here? So you can go to AI modulo Q, and then you take a modulo with P, or you go to AI modulo Q, and then you take a modulo with P. So now you see that now it is getting a bit complex. So now there are a lot of modulo involves, and you have a gut feeling that sure, some of these might be simplified further. So instead of applying some mathematical formulas and trying to simplify it, let's build our intuition for these kind of problems and see how do we handle modulos. So let's look at the number line, and you will recall that the problem mentions that P is less than Q. So on the number line, suppose this is P and this is Q. Let us look at the first branch. So in the first branch, you have done AI modulo P. So let's forget about all the mathematical formulas and complications, and let's look at things from number line and from a visual perspective. So AI modulo P, the first property of modulo is modulo X will always belong to the set 0 to X minus 1. So some of you might not know this fact, but like I said, in an ad hoc problem, even if you do not reuse the entire problem ideas, there will be some bits that you can definitely reuse in future problems. So if you did not know, then this is one learning for you, that whenever you take a modulo, the result will always be strictly smaller than the number that you have taken a modulo with. So you can already see that AI modulo P must be in this area between 0 to something less than P. Now, what happens if you take a modulo of any element in this area with either P or Q? So you can see that P and Q are to the right hand side of this number on the number line. So this is your second learning. So the second learning is that X modulo Y is equal to X if X is strictly less than Y. So modulo operations are a no op if the number that you are taking the modulo with, that is bigger. This means that once a number lands into this green bucket, no matter how many times you take the modulo with, whether it is with P or whether it is with Q, the answer will remain same. It will only, this element will not change. So this means that for this, once you have taken the first step towards this AI modulo P, this is the absorbing state. This cannot change any further. But what about this one, AI modulo Q? So for AI modulo Q, you can notice that it will fall in this area, an area that starts from 0 but ends to the left of Q. So there can be two cases. Either it lands in this area on the left hand side of P, or it lands on this blue bucket which is in between P and Q. So if it lands in this bucket, but if it lands in this bucket, the one that is on the left hand side of P, then you know that taking the modulo again with P is a no op. But taking the modulo with Q is also a no op. Why? Because this entire result is strictly less than Q, right? So this should be Q. This means that after this, the only possibility that could change is if it landed in this bucket between P to Q. So if the modulo the modulo the first time that you took, if it landed over here, then it can go from here to here, and once it goes here, it gets absorbed, because after that, no matter if the modulo is being taken with P or with Q, the answer will not change. This means that one element can only have a maximum of 2 steps. So you can see that if you have AI, it can either go through route 1, where you simply do AI modulo P and feature operations are a no op, or you can go this route where you do AI modulo Q, and then you make one more step to go AI modulo Q, AI mod Q, and then you take a mod with P. And why are both of these terminal operations? Because of this modulo P. Because once you have applied a modulo P, and if this is the number line, this is P and this is Q, you know that after applying modulo P, the number will be strictly less than P. It means that it is also strictly less than Q. It means that feature mod operations do not affect it. This means that the answer to the final problem will simply be minimum of this value and this value for any index, right? So now you can notice that once you have arrived at this stage modulo P, and at this stage you can keep on applying any operation that you want and your answer will not change. So that is why this is the minimum that you can achieve. But you have to be careful that if you apply modulo P first and then you apply modulo Q, then that is a no op, as we discussed over here. So that's why if you really want to go the route 2, then you have to make sure at all cost that the first operation that you apply is modulo Q. Otherwise, if you accidentally apply modulo P, then you are done. You cannot increase it any further. So let's define two arrays. We'll define the root 1 array, root 1 of I is equal to AI modulo P. Okay, and we'll define root 2 of I as AI modulo Q and then modulo P. And then finally you define root min of I is equal to root 1 of I and root 2 of I. And in this manner, the answer will simply be summation of root min of I for each index, because you are independently minimizing the final value for each index. So this was the first version of the ad hoc problem, where we learned a bit of tricks about modular arithmetic, and the tricks were that modular arithmetic with any number has to be strictly less than that number. Second thing was that x modulo y is equal to x, it is a no op if y is greater than x, and we had a beautiful proof from the number line, visual proof. All of these math you can also prove rigorously on paper. But what is more important from these ad hoc problems, that you learn how to visualize numbers that deal with modular arithmetic on a number line. And then you saw that for each index, some states are absorbing. It means that no matter how many times you do this operation, because of this property, then the only two possibilities where it lands is it is AI modulo P, or a two-step process where you do modulo with Q first and then modulo with P. So you have to be very careful not to do the modulo with P first if this root 2 is going to give you the minimum benefit. With the root 2 is going to give you the minimum value. Now let's move on to the version 2 of this problem, where this time you are not allowed to do the operations independently on each element. Okay, this time the problem statement says that select a subarray of length greater than or equal to k, apply modulo p or modulo q to all elements of the subarray. So this time you are not allowed to minimize each element by yourself. The subarray that you select, all the elements of the subarray has to behave the same way. Suppose you have selected this subarray from here to here, then either you do all the elements modulo p or all the elements modulo q. Now from the previous analysis you know that doing modulo p first hurts you. It hurts your chances if root 2 was the preferable root for some of the elements. For example, in the array, suppose you had this original array, and let's paint all the elements that had root 2 as their favorable choices as blue. So this element had the root 2 as the minima, this had the root 2 as the minima, this had the root 2 as the minima, and this had the root 2 as the minima. Now if these two elements are not at a distance that is greater than k, or suppose they are at a distance that is greater than k, and if you have selected both of these elements in that subarray that is of length greater than k, and all of these elements had the root 1 as their minima choice, so they will want modulo p first. But this wants modulo q first. So there is a compromise to be made, because if you do modulo q or if you do modulo p first, then it will go into that root 1 and it will not give you the minimum benefits. So of course you want to you will have to do some trade-offs to figure out which element should get the benefit and which one should not. So now this is a bit tricky to handle, and in fact this is one of those problems where it is very easy to come up with correct looking greedy algorithms, but that might actually be incorrect. So what really matters in these kind of problems is the way that you think and your line of reasoning. So let's see how we can think in the correct direction without making unnecessarily greedy choices, and whatever we do we have to convince ourselves that it has to be correct. So remember, our goal is to still see, in an ideal world we would still like to have whatever root each element wants, we would like to provide it, right? But it might not be possible, because sometimes you will have to apply an operation on a subarray, and then some elements might actually land into the root 1 when instead they wanted to go into root 2, and there is no way to come back, because once you land into root 1 there is no way to come back to root 2, because these operations are not reversible. So you can see that there is some penalty that will be incurred once you start applying the operations on the subarray. So your gut feeling might say that, okay, we have to minimize the penalty, right? So if you have to minimize the penalty, you would like to disturb the minimum number of elements from their desired roots. And how do you do that? So let's now focus on the first operation. And this is another technique that you can use in future ad hoc problems. That is, when this problem is telling you to do a lot of operations on a lot of subarrays, and notice that some of them can be overlapping as well, right? So how do you solve this complex version? So you focus on one small thing at the time. So let's focus on the first operation. So suppose you have selected this block of length k. Sorry, not length k. I mean, we can't assume that it is of length k. So suppose you have selected this block of length greater than k, greater than or equal to k. Wherever this block might be, we are not applying any greedy choice right now. Then of course, all of these elements, they will already incur the penalty, because they will either go to root 1, where everything will be written as modulo p, or they will go to root 2, where everything will be written as modulo q. So now let's see what happens if all the elements go to root 1. So if all the element goes to root 1, you know that this state is an absorbing state, because the elements cannot change any more from this state. Because once you have gone to root modulo p does not change it, neither does modulo q. Okay. Now what about this stage? Some of these elements might have wanted to directly go to this modulo p stage, right, root 1, but you have decided to do the operation modulo q first. You have to make some choice. Either it is this one, then some of these elements will suffer, or it is this one, so some of these elements would suffer. So if you have already decided to go to modulo q stage, then you can see that you might as well complete your journey, because you are allowed to do any number of operations on the subarray that you have selected. So you might as well go to modulo q, modulo p. Why? Because once you have landed in the modulo q stage, you can notice that some numbers on the number line will be here in this section, and some number will be here in this section. So all the numbers that are in this section, if you take a modulo with p, their answer will not change. But all the numbers that are in this block, if you take a modulo with p, they will move to this block, so they will become smaller. So doing another modulo p doesn't hurt you. So if you have already done modulo q, you might as well do modulo p as well to complete your root 2 journey. So now this means that all of these elements have their final modulo as modulo p. This means that they have incurred the penalty, sure, but now no matter what operations you do on them, they will never ever change, because these are the absorbing states that we have discussed. So remember that you did not want to incur any penalty on any element, and you wanted each element to go whatever route they wanted, but it was not possible. So that is why you were investigating the first operation. But in these kind of problems, your gut feeling might say, or if you don't know, but then still, like, this pattern is very evident, that once you have paid some penalty for one subarray, do you really need to pay this penalty for multiple elements? So let's investigate that. So what about, so we have already paid the penalty for this subarray. What about the element that is present at this location? Suppose it wants to go to root 1. That is, it wants modulo p first, but for it to go to modulo p, it needs a subarray that can contain it and has length at least k. So we know that all the elements inside this subarray, all the elements here, they don't care now. After you have done this operation, they don't care what you do with them, because they will never ever change. So you can just extend this subarray to the right, and you can apply modulo p to the entire subarray. So these elements will not change, and this element will move to modulo p stage, right? So once it has moved to modulo p stage, you can think of this as one big subarray where all the elements are sitting in this modulo p stage. Okay, so now you know that the element that is adjacent to the subarray on the right, that can be converted to root 1 if it wants. But what if it wants to go to root 2? And root 2, wherein it wants to do modulo q first, and then it wants to do modulo p. So this is also possible. Why? You can still select this entire subarray, and you know that its length will be greater than or equal to k plus 1. And then you can apply modulo q. So these elements will not change. Why? Because of the fact that all the elements are in modulo p stage here. And this element will silently switch to modulo q. And then you apply modulo p to the entire subarray again, and you reach this stage. So this element gets merged into this. So if you continue this line of reasoning, you will realize that once this element is merged, and so these elements are in the modulo p stage, this is also in modulo p stage. Now what about the next element? So by induction, you can see that it follows that since this has become one big subarray, then this can provide this element with whatever it needs. If it needs R1, it can do that. If it needs R2, it can do that. Same for the elements on the left hand side. So if you focus on the elements on the left hand side, suppose this element, it wants the R2 route. That is, it wants to go to modulo Q first and then to modulo P. So we know that these array elements, they do not care what is being done to them after they have paid that penalty. Then we can just take this subarray, it has length k plus 1 or at least k plus 1, and then you can apply modulo q to this entire thing. This will not change, and this will change to modulo q, and then you can apply modulo p to this entire thing, and you will reach this. So this means that the first penalty that you pay, that is the first operation that you do, no matter how much it costs, after that you can definitely achieve your dream goal. Your goal was to get every element to its root 1 or root 2, whatever it desired. This means that you have to do the first operation, and that first operation can either be via this route or this route, right, for this entire subarray. So which one would be better, which subarray to pick? So now you can see that since you are paying the penalty for all the elements that are inside this block, so you want to minimize the block while still following the rules. So it doesn't make sense to select a block that is strictly greater than k. Why? Because you could have just selected a block of length k and then given this element whatever choice it wants for free by just paying the penalty on these smaller set of elements. So one thing is for sure, that the optimal algorithm is that you will have the first k element. The optimal algorithm might be first operation is done on a window of size k, right? And future operations can achieve min value for everything outside the window. So now which k length window do you choose? So if we have come this far, we don't really need to be greedy and then try to like choose the fancy looking k length window. We can just try out all of the windows, right? So if this is an array, you have to choose one window for sure and pay the penalty for it, right? So you try all the possible windows. So suppose you want to try the window that starts at I and ends at I plus k or I plus k minus 1, whichever it is. So if you want to find the answer for this window, all you need to know is what is the root min of the prefix, what is the root min sum of the suffix, and then for this window, how do you compute the answer for this window? So your penalty would be, ideally all the elements would be equal to root min, right? But either you add the penalty as root min of this sum minus whatever elements could not transform, or basically you do something like this. So for this element, for this window, you will either go via the root 1 or you will go by root 2, right? So your answer will simply be summation of root 1 and I to j, or summation of root 2 I to j, right? Because all of these elements, they will either be in the root 1 section or the root 2 section, and elements outside the window, they will be in their root min form, right? And you take whatever is the minimum at all the sliding windows of length k. So you check this window, then you check this window, and you check this window, and so on. And in this manner you can solve the problem in O of n with prefix sums, suffix sum, or basically any subarray sum. You can just maintain a prefix sum array that can query the sum of a subarray in O of 1 time. So now you see that we have not made any greedy choice at all, but did explore all the possibilities. And even though this is an ad hoc problem, meaning this exact problem setting you might never ever encounter again, but the ideas that I talked about in this problem you can definitely reuse in other problems, especially the modulo tricks, the modulo visualizations on the number line, and the fact that if you are asked to do some operation on a subarray, it makes sense to just visualize what happens after the first operation. Can you minimize the penalty? And by minimizing the penalty, we are not being greedy, because these elements have already paid their cost and they are at their modulo p stage. So these elements, they can help all the other elements. So these ideas, they are very frequent in ad hoc problems. So if you want to upsolve this problem, let me know in the comment section. I will link it down below. Thank you.